All right, so we have a lot to do today, but it may end up being split. You just got to bear with me. If it is split, I'll readjust your homework. Okay. So right now it's like normal. The next couple homeworks are not normal. I've put them in. You won't need your book at all for the next couple homeworks. Okay. But for today's, you will. It's normal. So we might just, I think there's 4 questions. So we might have to split it like 2 and 2, but you'll just have to turn it in tomorrow. Okay. All right. So we'll see how far we get. We're going to start with blocking completely randomized designs. Yes, I should turn that on. Good idea. They're the simplest statistical design. Okay, completely randomized designs are the simplest statistical design for experiments. There we go. Yeah, we're on the old ones. I told you you'll need those tomorrow, possibly. No. All right, they illustrate clearly the principles of comparison. Random assignment. Control. And replication. But just as with sampling, there are times when the simplest individuals that are similar. Wait a minute. Let me get on the right page. But just as with sampling, there are times when the simplest method doesn't yield the most precise results. When a population consists of a group of individuals that are similar within I can't write today, sorry, but different between a stratified random sample gives a better estimate than an SRS. The same logic applies in experiments. All right, so the idea of blocking, and you guys will see it in just a minute, is making a randomized block design to block for it. So like if you have a sample, like a SRS, but you want to block it, you might block it by gender. You want to see how it affects the males and affects the females. So I'm going to read this to you. You're going to have to listen. I didn't put it in there. It's too long. But if you want to look at this, it's on page 251. If you want to go back and check it out. All right, so suppose that a mobile phone company is considering 2 different keyboard designs, A and B, for its new smartphone. The company decides to perform an experiment to compare the 2 keyboards using a group of 10 volunteers. The response variable is typing speed measured in words per minute. How should the company deal with the fact that 4 of the volunteers already use a smartphone, whereas the remaining 6 volunteers do not? They could use a completely randomized design and hope that the random assignment distributes the smartphone users and non-smartphone users about evenly between the group using keyboard A and the group using keyboard B. Even so, there might be a lot of variability in the typing speed in both groups because some members of each group are much more familiar with smartphones than others. This additional variability might make it difficult to detect the difference in the effectiveness of the new keyboards. What should the researchers do? So they're going to block for those things. Again, so what's happening in there? They're testing keyboards, but they have 10 users. Some have used smartphones before, but some have not. Okay, so they want to make sure, obviously, if they've used smartphones and they've been texting, they're really familiar with the keyboard. If they have not been using smartphones, then they've not been texting and they wouldn't be familiar. So they want to block for that so that they can see which keyboard actually increases or is preferred among both groups. Okay. So the idea of blocking, a randomized block design, this is what they do. So we have couple things. This is just information for you. This is not really part of the thing. They have keyboard A and keyboard B. They had 10 volunteers. 6 used smartphones, 4 do not. And the response variable is the typing speed. In words per minute. So that's just a nutshell of what went on, okay? So underneath here, I'm going to show you the randomized block design. We made the experiment the other day. Let me show you. Yesterday, Tuesday. This right here, when we did this. But what we're going to do now is we're going to block before we random assign, okay? So we're adding one more thing in there. So we started with 10 volunteers. Remember, we always start with the experimental units. 10 volunteers. We're going to split them into 2 groups. I switched these 2 numbers. Fix them back. I switched these 2 numbers. 4 use, 6 do not. Sorry. We have 4 that use. This is what we're blocking. And 6 that do not. So now what you're going to do is follow back up with that experimental design. So we have our experimental units. We've blocked them. So what we're going to do now is random assign into 2 groups. One group is going to use keyboard A. One group is going to use keyboard B. How many are going to use A and how many are going to use B? Yeah. We're going to split the don't use by random assignment to use keyboard A and keyboard B. Anybody want food today? How many are going to do that? 3 and 3. So then the difference in the rest of it is that you're going to compare these 2. You're going to compare these 2 against each other. And then you're going to compare the 2 different altogether. Okay, so I'm going to go over it one more time. You have keyboard A and keyboard B. You have smartphone users. You're going to look again at blocking them. And why did we block these? Tell me why we blocked them again.
Because there would be a lot of variability.
Yeah, too much variation because there are some that use smartphones, which means they're obviously, y'all seen your parents type, okay? You've seen it. You've seen your parents text. Now, some are good. Correct. So let's go with your dad. Like, he would be one of the not users.
Yeah.
Does that make sense? Compared to you, who have used smartphones your whole life. So y'all are like, right? Y'all got what I'm saying? All right. So they want to block that out because there's too much variability in the way that Rachel uses her phone compared to the way her dad uses his phone. Okay. So that's why they're blocking. They're gonna decrease that variability. So they're gonna test all those non-users who should be at the same level, pretty fairly close to those that are at a higher level. Okay. So then the ones that use, they're going to check out between A and B, which one was better for the ones that do use. Then they're going to do the same thing for the ones that don't use. And then they're going to compare those results to each other. Okay, so compare. All right, flip it over. A block is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect the response to the treatment. In a randomized block design, The random assignment of experimental units to treatments is carried out separately within each block. Using that randomized block design allows us to account for the variation in the response that is due to the blocking variable. This makes it easier to determine if one treatment is really more effective than the other. Okay. To see how blocking helps, let's look at the results of an experiment using the 10 volunteers, 4 who already use a smartphone and 6 who do not. In the block of 4 smartphone users, 2 will be randomly assigned to use keyboard A and the other 2 will be assigned to use keyboard B. Likewise, in the block of the 6, A and B, each of the 10 volunteers will type the same passage and the typing speed will be recorded. Okay, is everybody good? So if we look at this, what do you notice?
The keyboard B typing speed seems to be slower.
Sorry, you should have yelled at me. You good?
It was just one word.
It's okay. Everybody else okay? Y'all tell me if I go too fast, all right? Okay, so when we look at this, we see that keyboard A's are shifted towards the right or to the higher speeds, where shift B is shifted towards the lower. So it seems that keyboard B is a little bit slower, a little bit harder to use, right? Slows them down, okay. So there is some evidence that keyboard A results in higher typing speeds, but the evidence isn't that convincing. Enough overlap. So again, like right in this area right here, it's about the same. So there's a lot that are pretty fairly the same. Occurs in the 2 distributions that the differences might simply be due to the chance variation and random assignment. So we're going to look at a couple more graphs. If we compare the results for the 2 keyboards within each block, however, a different story emerges. Among the 4 smartphone users indicated by squares, keyboard A was a clear winner. So these are the ones right here, are the ones that use smartphones, okay? We can see that it's way above. A is way above B, okay? Likewise, among the 6 non-smartphone users indicated by dots, keyboard A was also the clear winner. Again, the B is down here where the A's are above. So now you can actually tell with the blocking which one is better, okay? The overlap in the first set of dot plots was due to almost entirely to the variation in smartphone experience. Smartphone users were generally faster than non-smartphone users, regardless of which keyboard was used. In fact, the average typing speed for the smartphone user was 40, while the average typing speed for the non was 26. So it's a big difference, okay? To account for the variation created by the difference in smartphone experience, let's subtract 14 from each of the typing speeds in the block of smartphone users to even the playing field. So all they did was they took these blocks right here, whatever their speed was, and they subtracted 14 because that was the difference, or that was the variation between somebody that did use and somebody that did not use a smartphone. And if you look, what happened?
They started to creep closer.
Yeah, they're pretty much the same as the other ones, right? So we accounted for that variation and they start being really close to each other. This accounted for the variation due to experience, which reduced the variation in each of the distributions. Now there is almost no overlap. When blocks are formed wisely, it is easier to find convincing evidence that one treatment is more effective than another. The idea of blocking is an important additional principle of experimental design. A wise experimenter will form blocks based on the most important, unavoidable sources of variation or other variables among the experimental units. Randomization will then average out the effects of the remaining other variables and allow an unbiased comparison of the treatment. The moral of this story, control what you can't, control what you can, block what you can't. So control what you can, block what you can't control, and then randomize to create comparable groups. All right, so we're going to work on a blocking example. Is everybody good with this page? All right, so when I actually make my design, I'm going to turn my page like awkwardly, but you'll just have to wait. It won't fit this way across. Like I said, I'm going to go diagonal across. All right. Women and men respond differently to advertising. Researchers would like to design an experiment to compare the effectiveness of 3 advertisements for the same product. Explain why a randomized block design might be preferable to a completely randomized design for this experiment. Why would they want to block?
Says they respond differently.
Mm-hmm. Perfect. All right, outline a randomized block design by using 300 volunteers, 180 men and 120 women as subjects. Describe how you would carry out the random assignment required by your design. Remember, there are 3 advertisements. 3 advertisements for the same product. 300 volunteers, 180 men, 120 women. So I'm going to turn my paper really weirdly so that I can go diagonal to diagonal. All right, so experimental units. Did you need it?
No.
Okay. You just kept looking weird. Experimental units. 300 volunteers.
Bother me to write that out.
You don't have to.
I'm just gonna write it small.
So we have 300 volunteers. They want us to block them. So how are we blocking them? We're doing women and men. How many women? How many men? I can't write really tiny because then you guys will be like, it's okay. What do we do to them? How? Say it again.
Divide the number.
Okay, but how? How do we divide them? What? Yeah. We're going to random assign into how many groups? 3. Why? We have add 1, add 2, add 3, add 1, add 2, add 3.
How did you figure out that you had 3 again?
It says it up here, 3 advertisements.
Oh, okay.
It's okay.
I was looking for the number 3.
No, it's okay. So how many in each group for the women?
40.
40. How many for the men? Is everybody okay so far? All right. What do I do then? Okay, compare the women. You compare the men. And then you compare those. Okay, we're not done with this problem. What did it ask you to do? Describe what? How you would carry out the random assignment. So we know 3 ways to random assign. What are those 3 ways? CAT method, technology, or table D. Is everybody good? So we got to pick a way. So I want you to pick your calculator.
I still don't know how to do it.
Well, that's what we're going to talk about. What's the first thing we got to do?
Well, you have to do it 2 different times.
Oh, you do have to do it 2 different times. Why?
Because you block them, you can't just
Right.
assign.
So talk about one to begin with. So let's start with women because we chose those first. Okay. So what would we do?
Assign each woman.
Numbers what? 1
1, 2,
through 120. Because we're using our calculator, we can do that. What if we were using table D?
0,
0, 0, 1 to 120. Is everybody okay with that? All right. And I would pick what in table D?
Just a random one.
A random line, but how many digits?
Oh, 3.
3 digits each time. It's going to suck really bad. Don't pick that. Okay. If they tell you to describe one and it's like 3 digits, calculate it. It's 100% always. Okay. It's much easier to do that than it is like if they ask you to pick the first 5, it might take you forever doing 3-digit numbers. Okay. All right. Label, sorry, it probably should say women. Numbers 1 through 120. Use your random integer function on your calculator. To choose how many? 40. What do you got to remember? Non-repeating and what? No, that's non-repeating. Within the range. Perfect. Within range. And what do you do to these? These will see add 1. Repeat. Process. To get next 40. Non-repeating. In range. To assign. To add 2. Rest, we'll see add 3. That's just women. Now you have to do men. How will that paragraph change for men? Absolutely. Instead of 1 to 120, it'll be what? 1 to 180. And then we're going to choose how many? Good. So the only thing that's going to change are the numbers. I'm not going to make you write it all out, but that's why I told you you're not going to have enough room. All right. Is everybody okay with that? You're gonna have to know how to do this. It's going to be on your test. I guarantee it. Okay. Is everybody good? All right. Rachel, you got it? You're not lying to me. Is everybody else good? All right. Matched pairs. A common type of randomized block design. For comparing 2 treatments. is a matched pairs design. The idea is to create blocks by matching pairs of similar experimental units. Then we can use chance to decide which member of a pair gets the first treatment. That is the random assignment of subjects to treatments is done within each matched pair. Just as with other forms of blocking, matching helps account for the variation among the experimental units. Sometimes each pair in a matched pair design consists of just one experimental unit that actually gets both treatments, one after the other. In that case, each experimental unit serves as its own control. And we'll go over all of this, so don't worry about it too much. The order of the treatments can influence the response. So we randomize the order. So you don't have to randomize the units because they're getting both treatments, but you have to randomize the order in which they get them, okay? So get your heart beating. An AP Stats class with 24 students performed the activity. We'll analyze the results of their experiment in the following example. So standing and sitting pulse rates, they took their pulses standing and sitting, okay? So each person did it, all right? A Fathom dot plot of the pulse rate for their completely randomized design is shown. The mean pulse rate for the standing group is 74.383. The mean for the sitting group is 68.33. So the average pulse rate is 6.5 beats per minute higher in the standing group, should say is. However, the variability in pulse rates for the two groups creates a lot of overlap in the dot plots. These data don't provide convincing evidence that standing pulse rates tend to be higher. So what they thought was if you're standing up, your heart's going to beat faster than if you're sitting down, okay? When we pretty much know you have to actually be active to make it happen. Stop. Stop. So everybody got it? All right. Flip it over. I didn't think we were going to get done, but we did good. What about the class's matched pairs experiment? The Fathom dot plot shows their data on the difference in pulse rate, standing or sitting. For these 24 students, the mean difference was 6.8 beats per minute. In addition, 21 of the 24 students recorded a positive difference, meaning the standing pulse rate was higher. So what they did the first time, because I didn't read you the problem, is that they split them in half, and they had some stand and they had some sit, and they took their heart rates, okay?
That would be the same type of group as the male and female, right? Same idea?
We didn't block, we just randomized. So we did a completely randomized where I picked, like if we were in here, I randomly pick half of you to stand and half of you to sit and we record. That's it. Okay. What they did the second time when they did matched pairs is they made you sit and record, and then they made you stand and record. Does that make sense? Everybody got it? Okay. So what they found out was that when they did that, everything was more together rather than overlap. But everybody also found a positive difference, which means that their standing heart rate actually was faster than their sitting heart rate. Does that make sense? All right. So notice in the example, we use the same scales for both graphs. This is to help you compare the amount of variability in the response variable for each group of the two experimental designs. Blocking by subject in the matched pairs design greatly reduced variability in the response variable. That made it easier to detect the fact that standing causes an increase in pulse rate. With a large amount of variability in the completely randomized design, we were unable to draw such a conclusion. Another important lesson to take away from the example is this: the design of the study determines the appropriate method of analysis. All right. I literally think it's like 4 problems, but don't be surprised if a couple of them are like that last example, where you have to make your own experimental design, and then you have to talk about how you would randomly assign.
Can we write it like how you wrote it in the homework?
Yeah.
Just like and then change the number.
You need to write it all the way out. I know it sucks. I'm sorry.
Can you show us how to do the random variable function? I really
Yeah, I'll
can't
show you.
find it on my calculator.
All right. I'm gonna stop sharing, stop recording.